The more particles that are in a solution, the greater is that solution's osmotic pressure, which is the tendency of water to move through a semi-permeable membrane toward the compartment that has the greater number of particles. And it does this in order to equalize the concentration of particles on both sides of the membrane. The concentration of particles in many types of human fluid corresponds to a sodium chloride concentration of 0.9% weight per volume. This is called an isotonic concentration, where iso means the same, and tonic refers to the osmotic pressure. If the concentration of particles in a solution is greater than the number found in body fluids, the solution is called hypertonic, and if it's lower, it's called hypotonic. Some types of medications are prepared as isotonic solutions to minimize the discomfort their osmotic pressure would cause in forcing water into or out of body tissues and cells. So this is particularly true of medications that are ocular, nasal, or intravenous. 0.9% sodium chloride is on our list of common intravenous solutions. It's also called normal saline and is isotonic with blood serum and with tears. If we wanted to prepare 1 liter of isotonic solution using sodium chloride, a quick proportion would show us that we need 9 grams of sodium chloride to do that. So there's our isotonic concentration, 0.9% weight per volume. How many grams are needed for 1,000 milliliters? We can cross multiply, divide, and the answer is 9 grams. All right, so we would put 9 grams of sodium chloride into a container and then add enough water to provide 1 liter of solution, and that would be 1 liter of isotonic normal saline. So the calculation didn't tell us how much water to add, but we knew that the solution volume needed to be 1,000 milliliters, so we would add enough water to reach the 1 liter line on the container. We learned from the day 1 slide set that the number of osmoles, which are the moles of particles, that are in each mole of salt differs depending on the salt's molecular formula, how many ions it has. So salt molecular weights, which represent the number of grams it takes to give a mole of each salt, also differ and are dependent upon the molecular formula. So as a result, not all salts are isotonic with body fluids at a concentration of 0.9% weight per volume. Each salt has its own concentration where it's isotonic. The most common way to derive isotonic values for different salts is not to calculate osmoles directly, but instead to use a conversion factor called an E-value. The E-value tells how many grams of sodium chloride it would take to equal the number of particles produced by 1 gram of another salt. So here's the E-value for potassium chloride. This value says that it would take only 0.76 grams of sodium chloride to provide the same number of particles in solution as 1 full gram of potassium chloride. The calculation at the bottom of the page shows how the E-value can be used to determine the isotonic concentration for potassium chloride. Again, the isotonic concentration is going to be different for different salts, depending on their E-values. So the isotonic concentration of sodium chloride is 0.9%. The E-value for potassium chloride is 0.76 grams of NaCl per 1 gram of KCl. We can find out how many grams of KCl it takes to be equivalent to 0.9 grams of NaCl, because 0.9 is the number of grams per 100 mils for an isotonic sodium chloride solution. So cross multiply, divide. The answer is it would take 1.2 grams potassium chloride to equal 0.9 grams sodium chloride. So we can take the expression for the isotonic percentage of sodium chloride and replace sodium chloride with potassium chloride, we get 1.2 grams per 100 mils. And so that is our isotonic concentration of potassium chloride. So E-values have been derived from many different kinds of salts. And you can use this table, which is from a pharmaceutical calculations book, for practice problems. You don't need to memorize E-values for the assessment. Remember that the E-value is the number of grams of sodium chloride it takes to equal 1 gram of another salt in solution, and not the other way around. For example, this E-value here, 0.25 for hydroxyamphetamine, tells us that we need 0.25 grams of sodium chloride to equal 1 gram of the hydroxyamphetamine salt.